Hello, and thank you for joining this session today. This presentation is a very practical approach in trying to utilize different kinds of loop measurements to actually get more information about the power supply plant. So the plant itself is the fundamental data we need to set up any kind of control system, and everything we need to know is hidden in that transfer function somewhere. As we have seen, there's also, let's say, extracting parasitics from simulations, and simulation is really vital, and it's usually a fixed part of the circuit design itself. But at some point, even the best simulation requires some verification. So eventually, there's not really a way around measuring the plant at some point during the design process. So what I'm trying to do with this presentation now is to give you some ideas how to tackle common practical challenges when you're trying to measure the plant transfer function of a power supply. And in particular, because due to the enhanced capabilities, most of the presentation is mainly focusing on digital power control applications, where we have just more tricks we can apply to work around some certain physical challenges. So first I will start to have a short review about the system modeling challenges and what is it what we can find in plant measurements which might be hidden in simulations, or what considerations you have to make when you look at simulation results versus real-world measurements. The second step then is we're shortly going to revisit frequency domain design approach, including so what is the kind of information we need to extract to be able to set up a good control system. And then eventually we go into the practical examples about how to conduct the plant measurements in different environments. Okay, let's start with why measuring the plant is a good idea. I mean, the plant transfer function, as I said, is the fundamental building block of every control loop design. So we need most accurate information, the most accurate information we can get. So unfortunately, the plant transfer function is quite sensitive to all kinds of different parameters. So first of all, obviously, the passive reactive power filter circuit components, the L's, the C's, but that determine pole and zero locations of the main filter. But then also the excitation method. So how do you excite that LC filters, and in their various nature really matters and has a huge impact on how your plant will respond. So this includes the accommodation. So it is a difference if you have an asynchronous or a synchronous converter, if it's just a half bridge, if it's a full bridge, a phase shifted full bridge, if it's frequency modulated. The control mode also counts. Is it voltage mode, peak current, average current mode? So there are many different ways how to operate one and the same power supply, which all of them might result in a fundamentally different transfer function. So then auto operating conditions also obviously are playing a big role. So the voltage potentials you have at the input and output also eat into, or let's say, define the gains, and the gains eventually result in different crossover frequencies, phase angles, and so on. And then eventually, last but not least, is the load. So every control system has its own characteristic, depending if it's in discontinuous mode, in critical conduction, or continuous conduction mode. So hence, we need to have a really good understanding how our power supply will behave, depending in which conditions we are operating it. And what is also very important and often missed in simulations is that a switch mode power supply is not a continuous time domain filter. That means we have to consider some set domain or some discrete time domain influences, especially in the high frequency range of the transfer function, which will then degrade the phase, give us less headroom for stability, and all of that needs then to be taken into account when you're setting up your control loop. So the common design steps start usually with you start to design your circuit, and that already includes the simulation part. So might it be just for first assessments of peak currents, and so that you that you design a circuit that is capable of matching the design requirements in terms of performance, bandwidth, and so on. And then you build the hardware, and the first steps is always making sure that the hardware works. And this is usually does not require a control loop. If you have the capabilities, you're operating the PWM and the switches so that you can see the circuit working, and then you work through all the issues you might find, like noise and so switch noise, maybe some noise issues in feedback signals and so forth. So you fix your hardware issues, and then at that point, this would be the point where you start to close the loop. Before you do this, however, validation the simulation results is highly recommended, so that you can make sure that all the idea you have about the circuit you have designed, which is mainly coming out of the simulation and the circuit design process, actually adds up, and that you don't miss anything, any differences between the real hardware and the circuit you have designed. And then eventually, when that is done, then you have all the information you need to safely close the loop. And then even if you have a really big power supply, it's a really safe and pretty straightforward process to power it up for the first time, close the loop, and you can make sure that, hopefully, fingers crossed, nothing explodes. So afterwards, feature development usually happens. This is where you then really tune the design for your final design specifications, so performance test and optimization, and eventually a design validation report or DVT report might be required. And in this report, again, having real measurements and validation results of the simulation results is also a really good adder, especially when you hand off the design to someone else, or let's say another design group is then taking over the maintenance of this product family. Good. So what we are looking into mainly is this phase during the design process now. So what challenges do we commonly have when we are starting to design our circuits? So when you use simulation programs like Simplis, or many of simulation applications allow you to make quick assessments of the frequency domain of a circuit. However, most of them are considering the circuit just as a continuous time domain filter. So hardly any one of them is really considering the switching process of the switch mode power supply. So, and unfortunately, this means that during one switching cycles, there's only one moment in time where the power supply or the power filter is actually capable of delivering power to the output. And you have to go through one control cycle and one switching cycle until the next chunk of power is delivered to the output. So that that chopped behavior of how power is delivered to the output, that implies a discrete time domain characteristic on top of our continuous time domain frequency domain. So what we see here is a simple buck converter where the simulation result suggests that the phase is actually pretty high here in the higher frequency range, and the ESR0 at the end of the output capacitor is then even pulling up the phase and giving you this huge phase region, so into the high frequency range. The reality, however, is that due to the switching process, the phase erodes, and the erosion starts pretty much at the resonant frequency and then gets more and more dominant over frequency until it drops into the Nyquist abyss at half of the switching frequency. So if we are considering that this is just the plant where the gain is falling too steep with roughly minus 40 dB per decade in this example, the desired or expected crossover frequency, which would be possible with this design, would be somewhere here in maybe the 25 to 30 kilohertz range. And if you look at the phase at this point, we already lost a lot of phase. So that consideration needs to be taken into account when you set up your control system, so that you know how far you can push the envelope in terms of bandwidth. When you're using simulation programs that have this continuous time domain simulation as a default, so before you go through great length in just making the simulation environment understand what it's actually simulating, It's also a very easy equation which can be used to just superimpose the phase erosion afterwards. So the equation you would have to apply is you have is minus 360 degrees times the frequency along your simulated range over the switching frequency. And that would then incorporate that phase erosion so that you can basically post-process the simulated data and get a more accurate phase angle. So what's also quite common, meanwhile, is when you're working on, let's say, more sophisticated power converter designs, high band gap devices, high switching frequencies, super high efficiencies, then power filters also start to behave differently than you might expect from previous experiences. So as a result, many of the common design rules or guidelines that everyone knows over time and never really questions are kind of outdated. So a good example here, for example, is the Dean Venables K-factor modulation. I mean, in 1981, when this was invented, it was a huge step forward because this was helping designers to incorporate an additional phase boost into their compensation network to compensate for the exact phase erosion we have just seen. So, however, the assumptions here are, because there is no real explanation how the phase erodes, what the K-factor modulation does, it's giving you a calculation how to tweak your pollen zero locations to compensate for an expected phase erosion. So that means that definitely only works for continuous time domain compensation networks, so analog feedback loops. Means this is not really applicable for digital designs, for example, and then it also assumes that the Q of the power filter is at around 0.5, ideally damped. So if you are working on designs with efficiencies greater than 92, 94%, so especially when you go really high up to 98% and further, this is way off. So hardly any of these rules, and especially also the math tools that were provided by Dean Venables back then, are just not adding up anymore. Then there are some further suggestions. Let's say, for example, there's a lot of myth around voltage mode controlled power supplies. So, for example, that there's a claim that they're always stable, because when you look into the continuous time domain of a voltage mode controlled power supply, then you have the complex conjugate pole at the resonance, so the phase folds down by minus 180 degrees, and then usually it's captured by the ESR 0 and pulled back up, so that the phase never really crosses the sole point of instability at minus 180 degrees. Unfortunately, this is not correct. So in many designs we see today, especially high frequency designs and smaller DC to DC converters, there is no ESR 0 anymore within the switching frequency range. So ESRs have dropped so far that they are usually in a way higher frequency range where they don't influence the relevant frequency range we are working in. And the second thing is that this claim that it always remains above 180 degrees or minus 180 degrees is outright wrong, because this is not a continuous time domain filter, it's a switching power supply, and thus affected by the switching process introducing this discrete time domain characteristic, which eventually will pull down the phase and make it cross minus 180 degrees within the relevant frequency range. So when we are looking at very high efficiency design, so for example, here is the development board with roughly 98% efficiency. That's a simple buck converter. But when you look at the planned transfer function of this design, then you see that the resonant frequency is super aggressive. There's basically no damping in the system left. So the last remaining damping comes from copper planes and maybe connectors, but that's pretty much it. So that means at the resonant frequency, your phase will almost drop almost instantly by minus 180 degrees. So it will hit the point of the sole point of instability pretty quickly. And what also happens is because the resonant point here, so the resonance itself is so violent and the impedance of that resonant tank is so extremely low that the vortex at which that oscillation takes place has an influence for quite a long time. So it pulls down the gain, and eventually the gain after the resonant frequency will drop steeper than expected. So usually you would expect it to the gain to drop with something like minus 40 degrees because you have this complex conjugate pole introducing kind of counterpart of two real poles. Each pole would introduce a slope of minus 20 dB, resulting in minus 40 dBs, but now we see something more like minus 55. So developing a compensation system that is then able to really capture this steeper drop of the gain sufficiently and also brings back up the phase here in this higher frequency range to get this converter up to reasonable bandwidth is quite a task and usually requires that you have to place additional poles and zeros here in the high frequency range. Good. Then when you're measuring the plant, you can also capture artifacts which might not be simulated or which you might not expect. So one of these artifacts was discovered here in this design. This is a 16th brick 300 watt power module, 48 to 12 volt. And so the two phases are operated 180 degrees out of phase. And so you have the two resonant points of each of the converter phases. But the two resonant frequencies also, due to extremely low damping and very high efficiency, start to add up. So at twice the resonant frequency, we suddenly saw this funny bump and jerk showing up. And eventually it turns out that this is yet another complex conjugate pole at twice the resonant frequency. And this is a quite nasty thing because it kind of interfered with the target resonant crossover frequency. So this became a real bandwidth limitation. And there was hardly anything you can do about it because this, again, the impedance at this point was so extremely low that hardly any polling zeros of the compensation network showed any effect. So they started to show effect slightly above and slightly below, but not at that point where we would have needed it. So, and this is because it was not discovered anywhere, not in simulation or any other measures. Really measuring the plant was the only method that actually exposed that issue so that we better understood what's going on, and then we could start to work around it with hardware modifications and modifications to the control system. And last but not least, it's also a very tricky thing sometimes to measure the plant or to perform any measurement, actually, especially in high voltage designs. So you have, for example, here on the left, we have a totem pole bridges PFC reference design where the points on, So where the points where you would have to connect the probes are hardly accessible and surrounded by high voltage components. So it will be very tricky to get your injection cables tied here somewhere between that heatsink and the switch bank and here the bulk capacitors. This down here, you have maybe half a square centimeter of space where all the probes need to go. And that's right in the middle of high voltage. So that's not very convenient. And giving that probes sometimes just slip and might just rob over the PCB, it's also really a safety hazard. Things are getting more tense as these designs start to evolve. So when we look at the next generation, and here we're seeing a multi-level, it's a 4-level PFC approach. It's still a totem pole bridges PFC, but instead of just one pair of high frequency switches, we now have 3 pairs. So, and the 3 pairs are then balanced with flying capacitors. So now it's getting even more tricky because the design shrinks significantly. So from 20 by 150 millimeters, we're down to 120 to 70 millimeters. And as you can see, because everything shrinks down, you have different ways in how you can build up that converter. So suddenly nothing, so here we have everything flat on the board, but here everything is getting vertical. So in this particular design, the access points we would need are just buried between two vertical PCBs, which are so close together that you hardly have any space at all to reach that point. So that is another example where things can really get tricky. And especially in these, let's say, modified topologies, it's absolutely vital to make this measurement, because simulation, again, can provide some degree of insight, but the truth is only revealed when you really look at the real thing. So that is kind of a big problem, and these are the kind of problems we're trying to solve in the further examples. So before we dive in, so I just would like to bring everyone on the same page, what we're trying to do and what the basic approach is. So when we are looking at any kind of feedback system design, quite simple. The closed loop transfer function is defined by the plant gain over 1 plus the plant gain times the feedback gain. So we have what we are looking at when we're performing stability analysis is only the open loop gain within the closed loop system. So that means we are observing if the product of the plant transfer function and the compensator transfer function is greater than -1, because at -1, that term would get undefined and that gain would just get infinite in theory. So the method we're doing is we're injecting a signal here to follow the theory. We're injecting a signal here into the reference and we get a response at the output. Both sinusoidal waveforms are compared. We're looking for differences in the peak voltage or in the magnitude, and which gives us the magnitude plot. And then we are also looking for changes in phase. So in the phase shift, and the phase shift is then plotted as the phase. So and here we have our Bode plot. So reality is slightly different because we are actually not injecting here into the reference. Usually we break the loop and inject it directly into the feedback path. So as a result, what we see in the measurement result is that the phase angle here is rotated by 180 degrees upwards, so that our measurement result is now not displayed between 0 and -180 degrees. So now it's starting at 180 degrees and going down to 0. So 0 is then basically the line where the phase would cross the sole point of instability. And so we're rather measuring directly the phase margin rather than the phase. But there's more, because the reference in real-world systems is also not located here between the compensator and the plant. It is actually the part of our error amplifier here on the right side. So this does not influence any measurement result, but it has some influence on what we can do when we are working with real implementations of real-world devices. So the compensation game, so the loop we're going to design now offers a couple of access points where we can basically slice down the problem and observe any component in that system separated from each other. So by default, in a classic loop measurement, we're just injecting here. The error signal will travel around the complete loop, and then we will see the response sorry, at the low impedance side of our injection point here directly at the output. However, if we have access to this point, so basically the so-called control to output transfer function, would then give us the planned transfer function. So this would be that part of that signal path. That would give us, when we are able to measure it, so when this point is accessible, we should see something like this, that we can then observe the planned transfer function. But we can also put our reference probe here at point A and the sense probe at point B, and the result, the measurement result we will get, is then our compensator gain. And then we can add both curves together, and eventually we will get an open loop, the complete open loop gain, and then we can put both probes back into this place and make a complete loop measurement and compare them. And then here we have basically fulfilled our sections of the open loop gain. So when we're doing things like that, then it's very important to keep in mind that the maximum differential input voltage of the Bode 100, so between channel 1 and channel 2, is limited to roughly 4 volt. I think the datasheet says something like absolute maximum rating of 7 volt, but considering that you really want to make a measurement and that you should make sure that you're somewhere in a safe range within the measurement range, I would not recommend to go beyond that 4 volt range. So if you use probes, scope probes with, I don't know, 10 to 1 or 100 to 1, what really counts is the voltage that remains here directly at the inputs. And so the divider ratios of your probes will definitely bring that voltage delta down. However, if you're working in high voltage designs and you're trying to make a measurement like from point B, which might be just at maybe 1 volt level, up to 400 volt here at point C, keep that in mind, that this is a tricky thing and that you don't damage your devices. So when you are using analog switching regulators, some of the PWM controllers have an access point where we can actually perform a measurement from the control to output. This is usually the case for every device that has an external compensation network. So it might be a general purpose device where you are tying the compensation network around the error amplifier, or it's a transconductance op-amp device where the compensation network would be tied to ground. However, at that point, that doesn't make a difference. This is the point B at which you would access your starting point. So this would become your reference. And then the sense probe would have to go to the output so they can observe the difference between these 2 points. So when we look into this, then it's also important to consider that everything that is actually driving your switches, so the complete switch node driving logic, PWM, comparators, SR latches, whatever might be buried in there, is actually part of the plant. And it is required to be part of the plant because this is the so-called PWM gain, which is then showing up in the measurement as the DC gain component. And that has a significant influence on where the crossover frequency is of that design. And when you're then at plant and feedback loop gain together, which then eventually gives you the correct point of the crossover frequency of the open loop gain. Things are getting a little bit more tricky if you have programmable analog PWM controllers. So one of our devices here, MCP 19117, has an integrated compensation network which can be programmed. So there is actually not any point available where you could get access to this control output probe point. So what we built into this controller is a multiplexer, which allows you to select that point and bring it out onto a test pin so that you can still perform your plant measurement from point B to point C. But you would have to actually enable this in software through a software communication command and enable that signal and route it out onto a test pin. And then you would also have the capabilities, but that might not be the case for every device of that technology. And last but not least, let's say now we're getting there where we're going to stay for the rest of the presentation, is digital control. In a digital controller, I have way more capabilities. So first of all, I have more pins. The devices are usually a little bit bigger, and they have additional peripherals I can utilize to give me access to any kind of different data point in my software block. So it means the easiest way, if we are still using a Bode 100 to measure the loop, we need an analog signal representation of any value we are going to observe inside the software. So the easiest way is always to use a DAC. So every device has DACs on board, and the DACs are quite fast, and they can be programmed with any kind of numerical value. So you can adjust it usually in resolutions up of 12-bit, and that is the resolution you can expect. And for the system itself, this makes total sense because this is exactly the resolution the device is capable to see when it's using an ADC converter. So an error signal that would be injected, let's say, in the common way by just using the injection transformer, and you're applying this error signal here to your feedback network, the resolution with which the error will be seen and received by the compensator is actually with 12-bit. And so the response is then, in this case, also given with the same 12-bit resolution. But even in a digital controller, we still have the clear separation between the compensator. So our point B here would be this point after the compensation filter. This would be the line we would pull out. And the PWM logic, however, then again becomes part of the plant. Again, introducing this DC offset PWM gain. Okay, so let's look at the final implementation. So when we are using this loop measurement and try to find a way in how to display the plant without having access to this point B. So if we would just like to use the common injection point on top of our output voltage resistor, for example, there are also ways. And I think the best method I know so far has been introduced by Ali Shirzavar in, I think it was 2010, could have been a little bit earlier. But the basic idea here is that you replace your feedback loop with a unity gain loop. So it means you have, instead of having the full frequency domain of your compensation network, you just have a unity gain block in there. And the last remaining part is then, the last remaining challenge is then how do I get the DC component? Because a unity gain, if it's really just a unity gain and I inject something here, I might get an error, but that error needs to be translated into some control output, which goes into the PWM, which is then introducing this DC offset. So if we're looking into our equation, however, that is then straightforward. We are just replacing our h of s with something that has a gain of 1. So eventually what remains is then what we measure is then only the remaining plant gain, and our feedback loop is completely transparent. So the solution here is we need a loop that is capable of considering the ratio between input and output. It's reproducing this ratio, a simple fixed constant gain, while the compensator itself is running in unity gain. So it's just passing the values through. So the implementation looks like this. So we are eliminating our digital filter and replacing it with a unity gain loop. That system, however, has still a couple of additional gains included. So one is the feedback gain, and the other one is the PWM gain. So the unity gain loop now uses this equation to drive the output kind of into regulation or close to regulation, so that we have the exact voltage ratios and the PWM is operating in the right point. And when you change something, then the loop is actually responding and trying to regulate the output, but in a very sloppy way with just a unity gain. It means every transient that's introduced will just pass through the system and show up at the output, and only this is then the system which gives us a good representation of the plant transfer function. So that factor we need, so this additional constant gain we need to build into this unity gain loop is then simply the ratio between output and input. So it's still just a transfer function after all. So the PWM gain over the feedback gain is the constant factor which is multiplied onto every error we see between the reference and the most recent ADC reading. And then we just add this to the previous control output, so that over time, when that loop is running and the error is big, it starts to build up an control output until the error is kind of 0, and then our output is in regulation, and that is then the condition we need to perform the measurement. So I put some of the all the math that's required to make the calculations here into the slide. But I would also like to use the opportunity to introduce you to a new software development tool we have released in last January. It's called PowerSmart, and that is actually an advanced kind of loop design supporting tool. So here we are representing different control systems by block diagrams. So you see the h of s, this is basically our compensator loop, and here would be the planned transfer function. And then here in between, you see the additional gains of the system. So here, this would be the feedback gain of current and voltage, then the ADCs, which are reading these feedback signals, the error amplifier, the loop, and then how the switch node is arranged to drive the PWM, which eventually then drives the plant. So when we are trying to set up a loop like this, then that tool also supports direct configuration without having to go through the cumbersome work and working out the numbers on your own. So in that configuration of this loop controller, you can enable this so-called p-term loop for plant measurements. This is the unity gain loop. And then you have fields for the feedback level and the control output level. And these tiny calculators here can be used and open other windows where you can choose between voltage feedback, shunt amplifier, current sense transformers, and different circuits. And then you get the option to enter your parameters, click OK, and then the tool will automatically calculate the gains and the respective binary numbers that are required by the software. For the output, this is a little bit more tricky because now it really depends on how you're driving your switch node. Is it a fixed frequency system, variable frequency, phase shifted? So depending on which kind of power supply you're designing and what your preferred computation method is, you just pick them. And then here on the left, these are the basic setups or features of the PWM of the device you're currently using. So in this case, it would be a DSPIC33C with a base PWM clock of 4 gigahertz. And then you just enter your switching frequency and you give a nominal duty cycle. And to calculate the nominal duty cycle, there's yet another calculation tool which allows you to pick if it's a buck or a boost or a buck boost type of topology, winding ratios, and then that software is really making a super high level quick assessment of the ideal duty cycle. So it's not too sophisticated what's happening here, but hopefully useful enough so that you can quickly move forward and set something up without having to work through a lot of science, actually. So when we're using this to set this up, then eventually the tool will calculate that factor and will it directly built into the code, and then you can generate the code and the code will then be added to your project, and you can program this directly into your design. And inside the code, now you have the choice to either execute the proper feedback loop or this unity gain loop. So both loops, so the code that is executing the loops do coexist, and then it's on the software to decide when and how to use either or of both. Okay, so one word of caution here. Because this unity gain loops, there is no compensation. So it means it is effectively a proportional controller. So it is not a robust control loop, and it's definitely not going to be stable. So the more sensitive your power supply is, especially the higher the frequencies and the less damping you have in the system, the more careful you have to be when you power up your power supply. So therefore, it's absolute necessary that the test conditions are super stable. So that you work with absolute stable loads. Best would be a resistive load, and no fast changes in input voltage. So you're turning it on, you slowly power it up under stable conditions, and then you just sit there and make sure that no big load steps will start to create oscillations which could potentially damage the power supply. Therefore, it's also recommended that inside the software you have something like a really slow soft start routine, and that all the protection you have in place before you actually power up the power supply. That means using comparators for current limitation, shutdown, fault handling. That all of that should already be part of the software to make sure that when you run it, it will not blow up. So the control loop itself also has this anti-windup block. So this is basically the numeric number block where you decide what your absolute maximums and minimum levels are. And when you perform this measurement, I would recommend that you make sure that these limits are really tight, so that it's, even if something goes out of control, that the control loop is better, that it saturates and the PWM kind of ends up in an open loop clamped condition rather than oscillating back and forth. Okay, so now we have basically set up everything and we can perform the first measurement. So the measurement here is the conventional method. So we are breaking the loop, putting an injection resistor in here in this example on top of our voltage divider, and then we use the B-bit to inject the error signal and we perform a classical loop measurement. So with this unit gain implementation, so so now you should actually see the planned transfer function. And now we come to this point of this presentation where I'm a little bit hesitant in running the live demo, because this was exactly what happened before when WebEx crashed. So therefore, I will definitely add the slide here so that you see the measurement result. But I would rather continue, if every one of you is okay, just to make sure that this doesn't happen again, that we don't have a break of 5 minutes. So if we can give it a try at the end of the presentation, if there's still enough time. But at this particular point, I would like to skip that step and dive into, let's say, the more interesting implementation stuff. Okay, so now this is basically how we measure the plant. This is a very basic example of how the plant gain is measured. So now we're coming to applying this method to more sophisticated power supplies and the options we have in working around some of the issues. So when we revisit this picture here, where we had the DAC that gives us access to internal data points, this is basically now the key feature we are trying to utilize for more sophisticated measurements. So the big challenges we have in super high density power supplies or high voltage designs is actually that injection point. So in the first step, we're trying to get rid of that requirement that we have somewhere in our circuit, buried in our feedback path, a specific location where we have to put in a component and where we have to put all the probes. So eliminating that is the major goal, so that we are pulling this over into some safe low voltage section of our design, which is easy or easier to access than the rest of the circuit, and especially the power filter section. So the way we're doing this is what we are doing there is actually where we're just moving the injection point. So now we still need to wire up our reference and sense probes. And the sense probe is the one that is most critical, because this is what eventually gives us our measurement result. And for that connection point, we're utilizing this internal DAC. So here we have yet another design example. This is a 1 kilowatt eighth brick, yet another design where it's really, really hard to make any modifications to the PCB itself. So there is also not enough space on that board that you can already prepare it to be measured. So tying in something like test points that are accessible with probes is really hard. Even if the SPIC sitting here seems to be fairly clean of components, if you look into the PCB, it's a complete nightmare. So just pulling out some test points is very, very disruptive for the design. So on a production level power supply, this becomes now quite challenging. So, but what we always have is an access point to the programming pins of the device. So because even in production, that device still needs to be programmed at some point. So usually what we have on the SPICs is called an ICSP, in-circuit serial programming port, which offers a data line and a clock line. And these two pins on purpose also happens to be analog inputs, so that you can use them to stimulate the software from analog signals, but they're also digital IOs, which can be used to route specific signals from the chip onto these pins. So this is really a service interface. It's not only covering programming and debugging, but also allows us to inject signals or to read signals from these pins. And this is the interface we're going to use here in this case, so that we can have a representative test interface, which is decoupled from the power part and easy accessible. So the only additional pin we need in addition to that programming interface, which is in place anyway, is the DAC output. So the DAC output might or might not be available. In this particular design, it is available. So here we can now hook up our Bode 100 by using the injection port to inject an analog sinusoidal waveform into either of these pins. And then we use the sense probe to sense the response from the DAC output. So, but there are also other designs. So for example, what happens if there is no DAC output available? How do we get access to, or how do we tell the Bode where we are? So there's another method we can use here, and this is instead of using the DAC, which is a dedicated pin on the device because it has an additional buffer amplifier. So there's only one pin available. And if you need that DAC output to drive some reference on your power board, like in case of this design here, where this pin is used to provide the reference for the current sensing devices, then we have to look for other options. So the ICSP interface can also be used, as I said, as GPIOs, and internally we can route specific peripherals to specific GPIOs. In this case, we are configuring an unused PWM channel, a high frequency, a high resolution PWM channel, and we route it onto our interface pins. And then we can use that as a DAC output. So the way we do this is we're configuring it approximately a megahertz switching frequency or PWM frequency. And then the value is then written as a duty cycle of that PWM frequency. This gives you approximately 12-bit resolution, which is the equivalent to what we would get with the analog digital to analog converter. So the beauty about this implementation is that no post filtering is required, because the Bode 100 does such a beautiful job in just filtering the signal by default, so that no further RC that would further influence, let's say, the transfer function we are actually trying to put out at this pin would further be influenced, is not required, because the Bode 100 does a beautiful job and just integrates over this PWM signal with exactly the right signal level, and it gives a perfect representation of the planned transfer function and the result pretty much exactly as we would see it with a digital to analog converter. The only difference here is the DAC here is pretty fast, and the settling time is roughly 150 to 200 nanoseconds, while a frequency of 1 megahertz always has this 1 microsecond delay. So that means you have another zero order hold in your signal chain, which will then make the phase erode earlier and the gain erode earlier. So what is required in any case is, before you perform the loop measurement, is to shortcut whatever you see at the input and shortcut it directly onto the DAC output, and then just run a simple calibration measurement where you can then see that the gain and phase run flat, and at some point they start to erode, and then you use this data to compensate, let's say, the phase and gain error you see in your final measurement. Okay, so this injection method is also a default option you can find on our CPU boards. So that these are our so-called SMPS plug-in boards. So they have been deliberately designed for switchable power supply designs. So they're equipped already, so they have nicely separated analog and digital I/O pins here on the card edge connectors. And then you also have all the required anti-alias filters at comparator inputs. ADC inputs are already built into that board. And then in addition, you have here on the upper left corner, this is the interface where you would wire up the Bode 100. So the pin number 2 here in the middle, the yellow one, this is where you inject that error signal directly into the ADC. Pin 1 is ground, and then pin 3, this is the DAC output where you read the response. Here on the right, we also have a communication interface built in. So it's a simple UART to USB or I2C to USB converter. And then here is the ICSP programming interface, so that when you're working on a development board or you're picking up a code example from a reference design, and that uses this injection method, and you have to basically pull it over from here to this interface, then you can make this on this DPPIM and then make sure that it works before you actually integrate it into the final firmware. So when you look into some of our reference designs, so here on the left we have 2 designs which almost look identical. They're a little bit different in size, but one of them is the 2.5 kilowatt and the 4 kilowatt total bore bridgeless PFC using gallium nitride devices from Transform. And as is already discussed, so the injection point would be extremely difficult to access and a little bit dangerous because it's right in the middle between high voltage components. And now if you look at how that DPPIM is plugged into the board, so that's safely isolated on the edge of the board, easy accessible, so there is absolutely no problem that you can place the probes safely, and everything is low voltage in this region, and therefore it's a quite easy task to perform this measurement. Where it really becomes interesting if you are working on designs like this one. So that is our 30 kilowatt Vienna rectifier reference design using our Microchip silicon carbide devices. And that's a different animal completely. I mean, there's when we're talking about 30 kilowatts, 800 volts, safety requirements are so high. Even if you just try to run this in the lab, it needs to be powered in a cage, actually, and at least 2 to 3 people must be present, and so forth. So it is quite cumbersome to perform any direct work on the design. And again, here, when you have a decent interface, which is good, nicely accessible, so the whole region on the board is free, can nicely be isolated, can be protected for the probes, and then you just access your low voltage pins and you perform your measurements. Okay, so some more details about this ADC injection. So practical application of it looks like this. So we are wiring up our output of the Bode 100 through the injection transformer. We use a resistor to turn it into an AC voltage, and that AC voltage is applied to an ADC input. Then internally, we are reading the feedback from the ADC, and whatever we see is directly copied over onto the DAC and pushed out to the sense output. So the influencing factor are the so-called zero order holds. So we have a time delay where the ADC here is picking up that error signal, and that error signal is also incorporated into our feedback path, which would usually be not the case. So I mean, usually we're just reading the result from the ADC and directly calculate the error and execute our compensation filter. But here we have this additional error injection sum in between. So we have the ADC sampling time, the ADC conversion time, and we have this most minute computation step in between, which then forms a zero order holder or some signal delay with which the error signal is getting injected into our signal path, internal signal path. The same is true when we read the feedback signal. So again, there's sampling time, conversion time until we see the value, or we can read the value from the register and push it over into the DAC, so that the DAC is then adjusting the output, which is provided to the sense input of the Bode 100. So we can shortcut this a little bit by utilizing things like direct memory access, so that every time a value gets updated here, it's getting pushed over to the DAC register automatically in the background, so that we don't have to use software to do this. So this minimizes the zero order hold a little bit, but it eventually doesn't make a big difference. So as I said, a reference measurement where only that path here, so you're injecting an error into this ADC, you copy it over onto the DAC, and you just make a reference measurement where you see the phase and gain erosion, high frequency, and then use this data to to compensate your measurement results afterwards in the post-processing. So, but there's still another more significant problem remaining, and this is when we are using this method in this way to create an AC voltage which is injected into an ADC, we have the problem that this is a true AC voltage. So it means it will drop below zero. So we have positive and negative voltage. Unfortunately, ADCs are single-ended CMOS circuits, so they don't support negative voltages. Or the maximum voltage we can support safely is roughly 300 millivolts. So that's definitely not wide enough to support a proper injection of an error signal. So we need some offset. And what I've seen a couple of times in various designs was that the people were using pretty much the same approach as we are using it with output voltage dividers. So there's a voltage divider which just divides the 3.3 volt input voltage range of the ADC down by factor 2. So you have an average offset of 1.65 volt. And then here the AC or the AC error is modulated onto that signal level. So the modulation works in exactly the same way. So you have your 5 or 10 ohm resistor sitting on top of this kilo ohm resistor network, and then the error is injected here. So the problem with this implementation is the 3.3 volt, which is now basically manipulated by just injecting a signal. Because the signal injection does not just travel this way, right? It's also becoming visible on the other side. So that means you suddenly see this injected signal not only injected into the ADC, but also in your supply line of your 3.3 volt. So, and modulating the supply voltage of a microcontroller with a sinusoidal waveform of significant size is maybe not a really good idea, because internally that voltage is then put on two different rails. So we have the digital rail and we have the analog rail. The digital rail is then connected to a 1.2 volt LDO, which directly drives the CPU and the RAM, while all our analog references, so especially the one from the ADC, is then also connected to that very voltage that is just tweaked and manipulated. So the error injection you're trying to achieve is actually not working that well, because it comes in with magnitude and phase delay, but it is coming in, and so that means that that error signal suddenly starts to influence our internal analog references as well as the feedback signal we are trying to oversample. So the outcome is undefined. It could be anything. So be cautious. Bad idea. The best implementation, however, takes a little bit of additional circuitry. So what we do here is still we built our voltage divider to create VDD half, or half of our ADC range. But then we use an additional op-amp where we have a differential op-amp which is adding the offset to that AC signal, and then the AC signal is adjusted roughly in the range of plus minus 1 volt max, so that it nicely operates around that offset. And that offset then, however, needs to be incorporated into our error injection. So because what we would like to inject is a pure AC component, so not that DC component. So that means what we have here added externally in analog needs to be subtracted back there in digital. And only then we have a proper sinusoidal waveform injection into our control system. So to determine that offset, because every system is different, not every 3.3 volt are super accurate, it is recommended to have a short calibration routine in the software. So when the device starts up, that it just oversamples that ADC input pin and tries to average a couple of samples to determine the real physical offset level of that signal, and use this later on then when you're performing this measurement. That op-amp here, that op-amp circuit is already part of the DP pins. So if you're using one of those to perform this measurement, it's already available. We are currently working on a test adapter where this op-amp circuit and the VDD half injection is already built in. So this offset management is already part of that tiny adapter, so that you can then directly access your programming interface like here with all the circuit you need, and you can directly connect the probes to this adapter. Okay, so this is how a measurement result looks like. So here, this is the measurement of the 2.5 kilowatt total pole bridges PFC voltage loop. So you see the measurement is quite accurate. If we compare it to the simulation, it matches pretty well. The noisy part here is kind of due to the limitations we have by just being limited to 12-bit resolution signals. So if you're using this averaging feature of the Buddy 100 suite, then you can clean this up over time. So this takes a little bit longer, but eventually it really gives you a perfect representation and a good databases to compare to your original simulation and calculation results. Okay, so whoops, there it is. Good, let's wrap up. So the measuring the plant is really complementary to the simulation, and it becomes a really important point in the validation of the system. And it also helps, especially in sophisticated high frequency or high voltage designs, to make sure that you know how to bring up the design and close the loop safely without creating any damage and smoke, and especially also for yourself, that your measurement setup is safe to operate. And the digital control allows you to especially achieve this by offering this different kinds of decoupled measurement implementations for higher safety, and also to measure inaccessible circuits. So I hope you found this interesting and helpful. I know not everyone is working with digital control, but maybe it gave you some idea. And if you have digital designs on your bench, then hopefully this was useful and enough practical tips for your daily work.